very romantic and very applicable, as I say. And you're going to complain that, well, wait a minute, we haven't done two Möbiuses of the same chirality, but we'll visit that. Because that one is, shall I say, disappointingly interesting. Or is it interestingly disappointing? It's not going to be something as romantic as this, but it is nonetheless quite baffling. But in the first instance, let's get to grips with why you get flat squares. There is a good way to think about this. You see, as usual in science in general and in mathematics in particular, sometimes if you take a good point of view, everything becomes clean and amusing. But if you take the wrong point of view, everything becomes ugly and really painful. So here is straight against straight. And we saw that if you cut this along the center lines, you get a flat square. But now let's understand why we get a flat square. Until now, in a silly attempt at theatrics, I was leaving the crosscut until the end. A good point of view, however, is to cut one of the pieces completely around without any suspense. And then, of course, it will remain for us to cut the other piece along the center line, and we'll attend to that in a moment. When we cut one of the pieces all the way around the center line, what you get is this. You get a pair of handcuff-like objects connected by a straight belt between, untwisted belt. So what we have to do is to cut this belt part along the center line, and at this stage I think you can already visualize what's happening. What are we going to get when we finish cutting this?
Square.
Because we are in this configuration, and when we open it you get a square. So you see where it comes from. It came from this. You can see that was straight against straight, cut open, and cut open, that's a square. So we now understand, we can visualize in our heads how this square comes about. How about straight against Möbius? That's actually an interesting case. We shouldn't make the suspense last. We should cut one of the pieces all the way around. Which piece? It turns out that it's helpful to cut the straight part all the way around. And we know that we get the flat square, and our job is to understand why we get the flat square. Okay, after we cut the straight part, what you get is this. You can visualize, right? It's a pair of handcuffs again, but this time connected by a belt which is twisted. Or if you like, you can have an untwisted belt, but now handcuffs on opposite sides of the belt. So now, so the previous case, straight against straight had handcuffs on both sides, on the same side, but here on this end and on this end. Okay. Now, what's going to happen if we cut this along the center line? That's the finishing job. But before we do this, let me work a piece of magic. I take this, and then I turn this around. So I get exactly the same thing as the result of two straight against straight.
And you're allowed to do that? That's not breaking any rules?
Well, who knows? But, you know, it's the same piece of paper. And I can start and finish it wherever I like. So if I cut this, I'm going to get the square. This operation that I have just, shenanigan that I have just performed in front of you, corresponds to the following thing. If I cut this along the center line, what you would get is not, in the first instance, a flat square, but you will get something like this, kind of a twisted version of flat square, like that. And all you have to do is to untwist it, and then it becomes flat. And that corresponds to this operation of taking this and then turn around, and here we are. You get another flat square. Okay, that's very nice. Well, it remains for us to try two Möbiuses with the same chirality or the same twist. Let's remember in which way we are making the Möbius. Let's twist it clockwise, and the other one also. Let's twist it clockwise. By the way, some of you might be worried, well, this is clockwise seen from this side, but if you see from this side, but it turns out to be the same thing. So, two of them clockwise. So you have two Möbius strips, exactly of the same chirality, glued against each other. I'd like to emphasize that this object is very, very symmetric. Two copies of the same Möbius strip, same including orientation, twisted the same way, glued at the right angles. So if I position it this way and turn it around this way, you obtain exactly the same thing. There is a symmetry there, rotational symmetry. On the other hand, cutting this object along the center lines is of course a symmetric operation. I mean, it doesn't distinguish left or right. So we are applying a symmetric operation to a symmetric object, and there's a widespread belief, indeed a conviction in science, that if you have a symmetric situation and apply a symmetric operation, what you get out is symmetric. Okay, let's see if that's going to happen. I'm going to cut this along the center lines, respective center lines, a totally symmetric object, and I'm doing a symmetric operation. And you'll see why I call it interestingly disappointing or disappointingly interesting in a moment. And I cut it all the way around. So here I go. I finish cutting everything. And what emerges is, first of all, disappointing because they separate. Oh, how unromantic, as opposed to the linked hearts before. But there is something really wrong about this unromantic object. You see, I got two pieces, and one of them looks like a boat. And this is what mathematicians like to call a two-gon, you see. N-gon, because it has only two vertices, it's a two-gon. And it looks like a boat. The other one is also a two-gon, but it's twisted in space, so you cannot actually untwist it, how do you try, into this shape. So, from a symmetric object cut along in a symmetric fashion, we got two objects that are not the same, asymmetric objects. How did this happen? It's really strange.
So how do you cut a Klein bottle in half? First thing you need is a diamond saw. Okay, here's a diamond saw right here. If I look along here, there's a diamond blade along here. Flip it on, and I can cut practically anything.